Dear audience, welcome to the third webinar in this series of EU-SysFlex webinars. My name is Hans-Peter Höschle from Energyville Vito, Belgium, and I'm the work package leader in the EU-SysFlex project. While the previous two webinars in May focused on the results of work package 2, the two webinars in June will focus on work package 3. The webinars of Work Package 2, focusing more on the technical scarcities, are available on YouTube to watch again or can be found via the website of the project. Today, as the first webinar from Work Package 3, we present the results of Task 3.2 entitled Conceptual Market Organizations for the Provision of Innovative System Services. Throughout the presentations, you will have the possibility to ask questions using the Q&A dialog at the bottom of your screen. We will collect all questions and address them after the presentation of the speakers during a consecutive Q&A session. If the questions cannot be handled during the sessions, we will come back to you via email. Let us now dive into the content of the webinar. I will start by giving a brief introduction to the EU-SysFlex project, followed by a quick outline of the objectives and tasks within Work Package 3. Let me then introduce the speakers that will discuss on their turn the most relevant topics treated in Task 3.2. This includes a discussion on when to use market-based or regulated organization, how to include grid constraints into a market organization, and the possibility and benefits to organize a joint procurement of several system services. Note that all findings presented today are under final review and will be made available soon as concise deliverable on the project's document website given by the link below. We expect the deliverable to be final by the end of the month, and we will keep you updated via all channels used by the projects. As you are all well aware, the European power system is in the middle of a transition. We aim at increasing the current shares of renewable energy sources from today's levels of about 30% to levels well beyond 50% in 2030 and further increasing. This mainly means the incorporation of large shares of non-synchronous sources of electricity. EU-SysFlex stands for Pan-European System with an efficient coordinated use of flexibilities for the integration of large shares of renewable energy sources. As such, it is the aim of the project to come up with new types of services that will meet the needs of the system with more than 50% of renewable energy sources. In the technical context depicted in the graph, Work Package 3 studies based on the technical needs of the system a continuous spectrum of innovative system services. A range of products and services is proposed to cover the range of technical system needs identified by the other work packages when assuming a future pan-European power system. The link between regulatory barriers and market design options, as well as product characteristics, is examined. To that extent, Work Package 3 will study the organization of markets and regulatory frameworks in the context of innovative system services. For different market design options, roles, responsibilities, and the interactions between stakeholders are challenged. The conclusions of Work Package 3 will support the construction of a flexibility roadmap on the one hand, and also describe innovative business models on the other hand. The EU-SysFlex project is organized in 12 interrelated work packages, and you will see Work Package 3 on top, addressing topics in a more generic way across all the demonstration projects. On this slide, you see the organization of the work packages and the 4 tasks. While basing our work on identified technical scarcities from Work Package 2, the work of Work Package 3 serves also as input in the business model creation, business case calculation, and demos, as well as Work Package 11. Finally, our results will move or find their way into the flexibility roadmap proposed by the EU-SysFlex project. The work of Work Package 3 is almost finished, and 4 deliverables are publicly available to present our work done in the last 2.5 years. Let me also take the opportunity to already invite you to the webinar next week on the results of Task 3.4, where we deployed advanced market models to quantify some of the points discussed today. The speakers of today are Przemek from PSE, Neith from Airgrid Innovation, Philip from EDF, and Jan Butke from Energy. I will now hand over to Sylvie from EDF. She was also the task leader and will give you now a more detailed introduction of the work that has been done within the task.
So thanks, Hans-Peter. Good afternoon, everybody. So as Hans-Peter just told you, I will shortly present you the main objectives of Task 3.2 and our approach. The slides reminds the objective of Task 3.2, and to sum up, the main objective was to assess different organizations to enable the system operators, TSO as well as DSOs, to get the services they will need in the future world. As reminded by Hans-Peter, this future world will be characterized by high shares of decentralized and intermittent resources that will lead to serious challenges to maintain the system in a safe state, be it at transmission or distribution level. To carry out that work, generic role models to describe interaction between actors were to be provided and be used as the basis for a comparison between different procurement arrangements. I would like to remind and to highlight that Task 3.2 should provide qualitative analysis and that quantitative analysis had to be conducted in another task, Task 3.4, as showed in the previous slide. So next slide, please. So here, this figure depicts our approach and the links between the other tasks of the project. So task 2.1 showed which scarcities will occur in the next year. Task 3.1 provided a list of relevant products to solve these scarcities and first organization proposals for their procurement. Lastly, Task 3.3 provided a framework for role models. Based on these inputs and on academic literature, and thanks to the expertise and knowledge of SysFlex partners, we described and assessed different arrangements to procure the selected generic products. These generic products are inertia, different frequency control products, voltage control, and congestion management products. At the bottom of the figure, you can see the outcome of the task that will be detailed later by next speakers. And now I will detail in next slide the different steps of our work. So first, we adapted the result of Task 3.1 and 3.3 to our needs, and we selected a list of generic roles, a list of generic products, and a first list of market organizations to be assessed. Then we described interactions between actors for the procurement of the selected products in the selected organizations with different optimization methodologies in the form of simplified role models. We assessed pros and cons of regulated procurement compared to market-based procurement. We spent a lot of time analyzing grid constraint management, as it was a complex issue with more and more congestion expected at transmission, but also at distribution level. Lastly, we discussed the advantages and drawbacks of joint procurement of several products. This last part focuses on joint procurement of FRR and congestion management products. So now I give the floor to Przemek and Niv to talk about market-based and regulated procurement.
Good afternoon. I will shortly talk about market versus regulated approach. We have two main approaches for procurement of system services. Market-based approach when we have the supply side, the flexibility suppliers who provide the bids. We have the demand from the system operator side, and this meets and the most competitive bids are selected and remunerated on the basis of some equilibrium price. We have also the regulated approach. When we don't follow this scheme, for example, the flexibility providers may need to be obliged to provide their services for regulated price. So this approach is characterized by lack of the market. We have some, in the existing system services market, we have some regulated aspects, and we could also have hybrid approaches when some providers may be obligated to provide the bids at some price, while other providers are free to offer the bids. Let's go to the next slide. When we look at the issue, we see that both approaches come in different flavors. In case of the market, we could have one entity selecting the flexibilities. In such case, we have the centralized optimization. We could have many entities selecting flexibilities that cooperate with themselves. In such case, we have decentralized optimization. We could have a situation when there is no designated entity for selection of flexibilities, for example, in the secondary market. In such case, we have the distributed market. In case of the regulated approach, in most cases, we have entity designated for selection of the flexibilities. It could be one entity. So once again, it's centralized optimization. There could be many such entities cooperating. And in such case, we have a decentralized optimization. Let's go to the next slide. When we look deeper, we find out that there are even more important parameters of the market that needs to be decided. We won't discuss them in today's presentation because we don't have time, but if you are interested, they are explained in the report. Next slide. And last thing I will tell will be about capacity and energy products. It will be important later on in the presentation and when reading the report. In case of the energy product, it is energy active or reactive, that is provided by flexibility provider and which is used by the system operator to ensure secure network operation. In case of the capacity product, it is the capacity that is reserved and held by the flexibility provider to provide the necessary response, the energy active or reactive. If it is necessary, we call it activation, and this activation is separately priced. We have different approaches to pricing of the activation. We could have a separate bidding of energy product, which is typical for the balancing products, like automatic frequency restoration reserve, AFRR, manual frequency restoration reserve, replacement reserve. We could have the fixed price that is set up in the capacity bid, or we could have generally fixed price, for example, including the price of zero, we don't pay. For example, it is typical for the FCR, frequency containment reserve. Some of the services come only with the capacity product, frequency containment reserve, fast frequency response. Some of the services come both with capacity and energy product, AFRR, RR. having only the energy product, it's not typical for the system services market. The most obvious example is the single day ahead coupling, where we have wholesale energy, but this is not the system services market. In some countries, the redispatching service has only energy product. And in our work, we saw one example of the country which has energy only product for the MFRR. And now I will give the floor to Niv.
Thanks, Szymek. Good afternoon, everyone. So Szymek has talked about the possible market organisations, and I suppose regardless of the market organisation, we've identified 4 phases of the product acquisition. The first is pre-qualification. So pre-qualification then is a check that the resource is compliant with the rules of the market for which it is applying. It mainly concerns compliance with the technical product requirements, so there might be a test associated with it. Also the financial requirements of participating in the market are checked, as well as any data communication necessary to connect to the platform. The second phase then is procurement. So for a market-based organisation, the procurement phase deals with the bidding for the flexibility, the clearing of the market, and selecting the providers that have been successful for provision. And such clearing then should always respect grid constraints. While I suppose the clean energy package states that flexibility should be procured in a market-based way whenever possible, there are exceptions. So I suppose there's exceptions allowed, so that for a regulated procurement, then there isn't competition on price as such, and units that have pre-qualified will be eligible for selection. The third phase then is activation. So this refers to triggering the use of the flexibility, and activation can be either automatic or manual, depending on the product. For automatic activation, we identified a few different cases. You could have self-activation triggered by the network state, so inherent activation or activation via an internal control loop. Or you could have an automatic signal sent by the system operator to an internal control loop. For manual activation then, an instruction is sent either by the system operator or the market operator, and then executed by the flexibility provider. The final phase then is settlement, and in this phase, the amount of the actual active or reactive power delivered by the flexibility is measured, and it's compared against the expected response. Then payments are calculated and processed, and also any data exchange necessary for other processes is carried out, for example, for imbalance settlement. So there are the 4 phases of product acquisition. And if we might just move on to the next slide, please. So we looked at when you'd use market-based and when you'd used a regulated organisation, and the criteria, some of the criteria considered are listed there. The first is compliance with EU rules, which is obviously important. There's a number of clean energy package and electricity balancing guideline provisions that are applicable. With regard to liquidity, we want to ensure that there's a market for the product that allows it to be traded at stable and transparent prices. Want to ensure that you have an organisation that mitigates strategic gaming and market power issues. You also want to ensure efficiency and short-term allocation of resources. So market-based solutions will generally be more efficient if there's sufficient liquidity and no market power. Suitability for investment then is another criterion. So ideally you want a solution that's suitable both for existing units offering flexibility and for new build units who want to invest. With regard to simplicity, market-based procurement and particularly a near to real-time market, although they're probably the preferred solution, will add complexity. So we examined where simpler approaches might be better in some scenarios. And finally then, the last criterion is transition costs. So interfaces for TSO and DSO coordination and interfaces with flexibility service providers from both a system operator and a market platform perspective have to be established, and obviously they have an associated cost. So we move on to the next slide there, thanks. So for each of the projects, we examined using these criteria what the best organization might be, whether it be market-based or regulated. And for frequency control products, there are a number of EU regulations, such as the Clean Energy Package and the Balancing Guideline, that require balancing capacity to be procured in a market-based way, unless it's a matter of economic efficiency or system security, in which case derogations may be allowed. There's also an applicable network code. But the conclusion was then that a market-based organisation should apply to frequency control products. With regards to inertia, then again, there is a preference for market-based solutions, but where it's not economically efficient, a regulated approach could also be used. And based on, I suppose, a particular product that was examined, synchronous inertial response, which was specified in task 3.1, a regulated approach might initially be preferable as only synchronous units qualify to provide that particular product. But in the future, the pool of providers could be expanded by non-synchronous technologies with grid forming control mechanisms. For voltage control products, there are strong mandatory requirements in the European network codes, and the choice between market-based and regulated might depend on the nature of the actual voltage problem. So voltage problems due to too high interfeeder consumption should be regulated, would be the recommendation, as the problem can only be solved locally. And voltage problems due to power flows in transmission distribution lines that are deviating from their foreseen operating range. In that case, a market could be considered for procurement, as more flexibility service providers can contribute to solve that issue. Thanks. And then the last product study was congestion management. And here the recommendation was that market-based solutions should be implemented in all cases where market power and strategic gaming can be sufficiently limited, and be that through competition laws or regulatory oversight. And the solutions then could include auctions to procure new capacities with long-term agreements, and or a market-based organisation for short-term allocation. However, if the liquidity is poor and strategic gaming can't be sufficiently limited, there may be an argument then to have mandatory participation with a cost-based remuneration for generation and voluntary non-firm connection agreements for loads. So just moving on to the next slide there, thanks. And finally then, just some general considerations to facilitate the participation of flexibility providers when designing, I suppose, an appropriate market organisation. We consider that the following elements should be included. The first is product characteristics. So characteristics should facilitate the participation of distributed energy resources, and would include things like shorter delivery duration or more frequent procurement. Aggregation then should be allowed wherever technically feasible. The third thing then is with regard to the FSP revenue. So the FSP should be able to stack up their revenues for different markets with sufficient certainty. To minimise transaction costs and to facilitate the participation of FSPs, the data exchange between all the different actors, be they service providers, MOs, SOs, the market should be as simple as possible, and with standardised products and interfaces where possible to facilitate cross-zonal or indeed cross-country data exchange. And finally then, a suitable pricing mechanism. So the Clean Energy Package advocates a pay-as-cleared mechanism as the default choice for balancing products. So that's preferred. But a pay-as-bid mechanism could be used in the case of low liquidity or where there's market power issues. Or also even a regulated pricing mechanism could be used in some cases. So in summary then, I suppose Shemek took you through at the start, the various mechanisms, the difference between market-based and regulatory approaches, and certainly for power systems with a high level of variable renewables, market-based approaches are generally preferred and indeed stipulated as the preferred mechanism in EU law. However, regulated approach is still needed, and in some cases it could be an interim solutions, and in other cases a long. So appropriate design is needed for the efficient development of flexibility markets, and yeah, there are a number of considerations for this. So thanks. I think I'll hand you over to Philippe next.
Okay, thank you, Niamh. Good afternoon. I try to, sorry. So I will speak of the different methods to manage grid constraints in the phase of selection, in the phase of procurement, which includes the selection of flexibilities. As we have said that we have completed a role model, and in particular, we have introduced a role. So role is a replicable responsibility of optimization operator, and by definition, this optimization operator is responsible for the optimization of bid selection, and it can use switching measures to solve grid constraints and satisfy the reserve needs of several products. So our main question is how to consider grid constraints, so both in current and voltage during the bid selection process. We have an important choice, so Shemek has showed that we have to choose between centralized or decentralized optimization. I will explain that in the following slide. And we will have another choice about which set of grid data will be sent by the system operator to the optimization operator. Three main options: a comprehensive grid data, partial grid data, so a subset of the comprehensive data, and bid limitation. That means not directly data about grid, but a constraint about the flexibility to be selected. So I will show you two diagrams. So the first one is about centralized optimization in the hypothesis of comprehensive grid data, so sent by the system operators to the optimization operator. You see here the main feature is that the optimization operator is one role, so thus for all the voltage levels, so it deals both with the TSO and the DSO and the other actors. So the system operators send, by definition, the comprehensive grid data and the reserve needs. The optimization operator assesses the grid constraints and select bids and switching measures. By only one optimization, he has all the data, and so he he runs, we'll see it later, but he runs only one optimization, and afterwards he sends his results to the other actors. And so, as I have said, you will see in the report variants with partial grid data. In one word, partial grid data consists mainly in sensitivities towards the important constraints to look after. In general, it works only for one topology. So in the standard case, it will be the present topology. And so, as I have said, you will see the diagram for big limitations. My other, so it comes. My other diagram is about decentralized optimization, still in the hypothesis of comprehensive grid data. So here you see that we have two roles: optimization operator for _T, so for transmission grid, and optimization operator for distribution. And so they collect the data needs in the same way as before. And each of these two, of both optimization operators, runs grid assessment and selects bids for himself. But afterwards, to make the system to work, a coordination is needed, because the first step of calculation can create temporarily a suboptimal solution. And so after this coordination, the result is sent by the optimization operator for transmission or distribution to the corresponding actors. Note that this scheme can work for one product, but as well for several products, and there are no consequences of the choice between centralized or decentralized optimization on the quantity of flexibility liquidity. So we have shown a discussion about the advantages of centralized and decentralized optimization. Of course, there are drawbacks, but the drawback of a solution is an advantage of the other solution. So here we have only advantages. For centralized optimization, the coordination effort between roles is lower because all the activity is concentrated in one role. So this is true in the hypothesis of comprehensive grid data. And so there is no iteration in the role model in the operational timeline. Of course, it saves time of coordination. By definition as well, the centralized optimization can achieve the completely optimal solution, because there is only one, all the data and the problem is concentrated. And so by the optimum solution, of course, is defined by the lowest flexibility costs for all the scarcities which are dealt by this solution. There is an economy of scale because here you have one place for the optimization algorithm instead of two or multiple places, and of course it reduces the cost in buildings to host a team or in hardware maintenance costs, for instance. And the interoperability concentrates on one interface to one optimization operator, so there will be only one set of rules. Then for decentralized optimization, an advantage is that a stepwise optimization is possible to consider particular requirements for specific voltage level or for a specific region. It will be easier to match localized solution to scarcities. In a localized solution, we mean a solution of which the description is not standardized, because that can be done without an optimization of the whole system. The individual algorithm, so the algorithm for each optimization operator is simpler. Less data is processed by algorithm. So each algorithm will have a lower development cost, and the individual algorithm will compute faster. Importantly, this solution fits to the current responsibility framework for system operators in the European regulation, because here there will be an allocated optimization operator for each system operator. And so there are less or no question about how to adapt the incentive regulation. And nearly, of course, the resilience will be higher, because if we lose one optimization operator, we have the other ones. In case of missing data, it doesn't prevent all the system to work. And in case of failures, note that normally the fallback procedure uses a decentralized optimization. So the normal procedure is closer to the fallback procedure. And then here it comes, quite important question as well, is which actor should be allocated for the optimization operator role. We have studied this question for different actors. So it could be each DSO and TSO. It could be a joint venture between TSO and DSOs, or it could be as well a commercial third party. And this problem has been studied for both centralized and decentralized optimization. And we have seen that all solutions are feasible. So our analysis is qualitative. It will be necessary to conduct a cost-benefit analysis to see all changes and risks, and of course to address national specificities. And the choice can be, in a specific situation, can be different according to the choice between centralized and decentralized optimization. But regardless, in general, regardless of the national situation, we find that if we allocate this optimization role to an actor, other than the corresponding system operator who is responsible according to the electricity directive. It would lead to significant challenges in governance and regulation. In our report, we put the first implications, but further research will be needed. So in the report, you will find a comprehensive table about this slide. And then to sum up, so first, for the choice between centralized and decentralized optimization, both can be applied for selecting flexibilities. Both methods can work with one or several marketplaces, and they don't reduce liquidity by design. Conceptually or theoretically, centralized optimization leads to an optimal allocation because it has all the data, but decentralized optimization can reach the optimum or a result close to it. It depends on circumstances. Circumstances, that means the kind of grid and design. Decentralized optimization is more relevant when DSOs need locational products, so a product with a particular and local characteristic. For inertia and frequency containment reserve, centralized optimization seems to be more relevant. And I remind that the optimization operator has to determine the optimal combination of switching measures and flexibility selection. We could allocate this role to other actors than the corresponding system operator, but this could cause significant governance and regulation challenges. So thank you, and I let Jan go on.
Thank you, Philippe. I will explain the chapter joint procurement. So at first, we must state that no single definition of joint procurement exists. In general, many different options are possible, and that is why we created an overview table to show the different options of joint procurement. The first line actually shows what joint procurement is not. Joint procurement is not does not exist if there is one system operator, so one buyer, which has one certain type of scarcity, which he solves only with one certain type of product. So, for example, if there is the TSO who has an imbalance problem and he solves it with MFRR, and for congestion management, he has got another product which he solves for another product to solve its congestions, or there's the DSO which procures a congestion management product only for themselves, but also does not coordinate with the TSO. Then we come to the different versions of joint procurement. Now, the first one is that you have got, for example, two buyers, two system operators who want to solve a certain type of scarcity with one certain type of product. Here there is the example of the coordinated procurement of congestion management by TSOs and DSOs. That, for example, the case for which Philippe just explained the centralized and decentralized optimization. So there's a coordination of TSOs and DSOs in order to create synergies and avoid any kind of conflicts. Then the next type of joint procurement would be that you've got not only one type of scarcity, but you might have two types of scarcities, such as imbalances and congestions. And there is one system operator which has got one product, for example, an MFRR type of product, for which he uses to solve congestions and imbalances. And he can do that in a coordinated process, so one after the other, for example, first congestions and then imbalances, or in a type of joint optimization across scarcities. The latter I will explain later how it can work. That case here of joint procurement could also work for DSOs, which use a congestion management product to solve like an active power product to solve congestions and voltage control in one step or in two steps. Then the next type of joint procurement would be that you've got, again, two types of scarcities. You've got one type of product, but you have now two system operators. And this is what we focus on in the next slides, which is also the focus of this task in the end, that we have got an MFRR type of product which can solve congestions and imbalances of both DSOs and TSOs in a coordinated or in a joint optimization. And then afterwards, there are also other type of joint procurements where you have not only one type of product, but for example, two type of products which solve one or more scarcities by one or more system operators in joint or non-joint optimization processes. Now I will explain in the next slide the motivation why we selected the joint procurement for congestion management and balancing /MFRR. The point is that there are current and have been recent discussions on this matter, also in the TSO-DSO report on active system management, which has been published last year. Then in some countries, some forms of joint procurement have already been implemented, such as in France and UK. And of course, MFRR and congestion management products can have similar characteristics. Both deal with active power, manual activation, and the full activation time and the duration are also similar. The advantages of this joint procurement depends on the versions. I will explain it in more detail later, but to give you a first flavor, a joint product could allow FSPs to bid only once to solve both scarcities. This might, for example, be appropriate in France, a few congestions exist. Or in addition, a joint optimization could also decrease the flexibility volume needed. So you optimize both scarcities in a joint algorithm, and that might, for example, be appropriate in a country in Germany, where you've got a higher likelihood of time and volume overlapping due to many congestions. The report describes, apart from the advantages, also the disadvantages based on the different versions. Now I would like to explain how synergies can be created, because it's not that an easy matter in the end. At first you see how they are not created. So here you see the separate optimization. On the left side, so the full picture shows, for example, one control or bidding zone. On the left side, you've got some generation and demand and an FSP. And the generation part on the left side transmits electricity to the load pocket on the right side, which creates an overload of here 1 gigawatt. And inside the load pocket, you have got some FSPs. One is pre-qualified for congestion management, and another one is pre-qualified for both congestion management and MFRR, so it's fast enough for both. And there you've got the situation that you have a sudden demand reduction inside the load pocket by 1 gigawatt, causing an imbalance. So if you want to optimize both scarcities separately, what do you do for redispatch? You normally ramp up generation inside the load pocket and ramp down generation outside the load pocket, selecting the cheapest flexibilities. And for solving the imbalance, you select the cheapest flexibility in the whole control zone, which is here FSP1. So in the end, 3 gigawatt of flexibility are selected. Perhaps you already assume how the synergies could be created. This is what the next picture shows. So you see that inside the load pocket, the picture above that, you have got an opposite direction of needs. One is the increase of the need to increase generation, but also the general need to decrease generation because of the sudden demand reduction. And this is this can be netted in the end, so that FSP3 does not need to be selected. And FSP1 also needs to ramp down generation then by 1 gigawatt. So that would then solve both congestion and imbalance and problems. So to sum up, what are the prerequisites to have to create synergies? First, you need a joint product such as FSP1 here, which is able to provide both MFRR and congestion management. You need an overlapping need in time and in volume, and you need an opposite direction of needs in a specific area, such as here the load pocket. When it comes to the process, the optimization must take place within the MFRR energy selection time frame. So all bits need to be selected close to real time and must be compliant with the MARI processes, and also with the congestion processes, of course. We also have elaborated this case for Germany. So we looked at figures from the year 2018. The point in Germany is that there is a regulated redispatch scheme, so regulated prices, which means the congestion management prices are a lot lower than the MFRR prices. And in the end, higher costs are possible since it is possible that the whole process is shifted to close to real time, and that is why you need to pick bits which are rather capable of MFRR to also solve congestions. And that is why in the end this is likely to lead to higher costs, so that in the end no clear net advantage could be detected in the end. I talked about the joint product. As joint product, we focused on the energy product near real time and not on the capacity product. The capacity product would probably also consider then the potential synergies of the energy product due to the joint optimization, but it was not the focus of our work in the end. And such joint products must be able to provide, as said earlier, both MFRR and congestion management, so must comply with the requirements of both scarcities. So the full activation time must be the same as for MFRR, so maximum 12.5 minutes, which could lead to the exclusion of certain FSPs which have a longer full activation or preparation time, such as cold generation, or also storage flexibilities or certain demand response, which first has to prepare in order to provide flexibility. Then the joint product also has to be as locational as needed in the end for congestion management. So an aggregated bid which includes FSPs inside and outside the congested area would not be feasible. And the product has to describe, if existing, the rebound behavior, so that the optimization can take this rebound behavior into account. This is necessary for congestion management because it can happen that an FSP first solves the congestion, but then has a rebound effect inside the congestion time frame, and then creates another problem afterwards. Of course, then you can activate another flexibility, but at least it must be taken into account, or it might be better to use another flexibility bit, which, for example, does not have a rebound behavior. With regard to the process design, we determined 3 different versions, which are quite distinct from each other. The first version is a coordinated optimization via a connected bidding. So at first, there is a bidding to solve congestions. So FSPs bid for this congestion management process, but they are allowed to, for example, tick a box and say that this bid might also be used for the following balancing process. So first, there is the gate closure time for congestion management, at least 55 minutes before delivery time. Why that? Because so far our assumption is that TSO-TSO, TSO-DSO, and DSO-DSO coordination needs at least 30 minutes time to find the best measures to solve congestions. And then there is the clearing of the congestion management process. And afterwards, the remaining bits are transferred to the balancing process. As said, only those bits where the FSP said that they would want that. And then in the balancing process, the FSPs, of course, may update their bits or place new bits towards the TSO 25 minutes before delivery, and then the normal process starts, which will also be part of the MARI process. So 12 minutes before delivery, that's the gate closure time for bits from the GSOs and the FSPs to do the cross-border optimization, which finishes 7.5 minutes before delivery, and then there is the flexibility provision. In the version 2, there is the coordinated optimization via a joint bidding. So 25 minutes before delivery, FSPs place one bid, which then can be used either for MFRR or for congestion management. So after that gate closure time, TSOs, DSOs check which bits to use for congestion management, and then the remaining bits are forwarded to the balancing process on national and cross-border perspective. And then in the third version, there is the joint bidding and the joint optimization. So again, there's the bidding for both MFR and congestion management, 25 minutes for delivery. But then, at least on a national basis, there's the clearing both for congestion management and for balancing in one process, be it centralized or decentralized optimization. So this is done to create the synergies, which I mentioned earlier. And then the remaining needs and bits are forwarded to the MARI process to do the cross-border optimization. Now I will explain the different the pros and cons actually of the different versions. We do that by comparing the versions with the separate procurement of congestion management and MFRR. So the base case is always the separate procurement here of congestion management and MFRR. First, the cost decreasing effects. There are effects of reducing transaction costs and increasing liquidity due to the possibility in version 1 and the necessity in version 2 and 3 to place bids combined for both scarcities. Then there's the potential of lower flexibility volume needed in version 3 due to the use of flexibility to solve both MFRR and congestion management. So that's the topic of joint optimization. And then in versions 2 and 3 can also decrease the strategic behavior because FSPs cannot choose between congestion management and MFRR. There are also cost increasing effects, meaning that it's also possible that liquidity is decreased compared to a separate procurement in the different versions, either because the gate closure time for congestion management is moved forward, that can happen in version 1, or because the joint gate closure time for congestion management and MFRR leads to the exclusion of certain FSPs, which can happen in version 2 and version 3. What can also happen is that transaction costs increase, or there's at least an increasing effect in version 2 and version 3, since some FSPs, which would normally only offer MFRR in case of separate procurement, then need to break down the aggregated portfolio to locational bids and also describe where this is necessary, the rebound behavior. Then on the next slide, the different challenges are described of the versions. So this does not show the marginal costs, but general challenges of the versions. So they could be overcome. Versions 2 and 3 at the moment show that the time frame is currently not sufficient for system operator coordination to find the best congestion management measure. And also there's no possibility to allow congestion specific solutions because there is the joint bidding phase and also in version 3 the joint optimization. So there must be always then one product design and for example one optimization across, for example, one time interval only, not across several time intervals. Then in version 3, due to the joint optimization, there's also a higher complexity of the algorithms and or the coordination between system operators because both scarcities are optimized jointly. And in that case, there is also the point that one flexibility bid is used to solve both congestions and imbalances, and this is currently not in line with a clean energy package when it comes to the cost allocation to congestion management measures on the one side and imbalances measures on the other side. With regard to transition costs, it are not possible to state anything because this highly depends on the national solution, which is already implemented. Then to summarize what I just said, from our perspective, the joint procurement of MFRR and congestion management energy product is a relevant option. It is possible, for example, to create synergies. It's possible to reduce costs, but it's also possible to increase costs, for example. So in the end, a quantitative analysis would be needed to determine whether joint procurement is superior to separate procurement and which specific version of joint procurement is superior to separate procurement. And when you look into the report, you see the German country case study, which did not reveal convincing benefits, but also other cases can exist. So in the end, you would say that such quantitative analysis should look on a national basis on the trade-off between the potentially decreased costs and the increased complexities. It must take into account the severity of grid congestions and MFRR needs, their cost structures, and also the existing processes. And then, of course, also some hybrid options might be possible between joint and separate procurement. And in countries where restoration reserve is used, also such joint procurement might be feasible, since there the time constraints are not that tight. So now I'm at the end of the joint procurement chapter.
Thanks, Jan. It's now time to conclude. So first I will sum up the main conclusion, but I will not repeat all the points raised by the previous speaker. So in a nutshell, we studied different procurement arrangements of generic flexibility services, and we assessed feasibility, advantages, and drawbacks of different options. We showed that market-based organization should be the preferred solution, but that in some cases, and depending on the product, a regulated arrangement could be justified. We compared different methodologies to consider grid constraints in the flexibility procurement, in particular centralized and decentralized optimization. We found that both were possible and that the choice depends on the product, among other factors. We discussed the allocation of the optimization operator role to each individual system operator, but also to other actors, like commercial third party. We showed that in that last case, significant regulatory challenges appear. Lastly, we showed that joint procurement of services, in particular for MFRR and congestion management, could lead to synergies. However, we also showed that the European framework with trans-European platforms for frequency control products imposes high organizational constraint to such arrangements. But as highlighted in the introduction of this presentation, this task, 3.2, didn't conduct quantitative analysis, and to adequately compare the different options, some additional studies would be necessary. I mean, quantitative studies to evaluate the proposed solution in real situation with actual structure of TSO, DSO, regulatory framework, existing processes of optimization, and so on. We have identified different issues to be looked further into, and so you have the list on this slide. First, we have the question of efficiency gains, and task 3.4 tackle this issue, and you can see the result next week during the webinar announced by Hans-Peter. Then we have investment or transition costs for the implementation of the new market design. We have temporal and computational feasibility with two questions. In centralized optimization, can a complex centralized algorithm provide results fast enough for all voltage levels and possibly several products in case of joint procurement? And the second question, in the case of decentralized optimization, can the coordination between the different levels be done fast enough? Then we have communication costs. The number of communication channels and data exchange requirements between different actors vary depending on the choice of optimization, centralized or decentralized. We have the question of allocation of the role to system operators or other actors, and the type and amount of grid data to be exchanged between actors. And lastly, the question of small DSOs should be examined. Small DSOs could carry out a cost-benefit analysis to assess whether an independent optimization or grouping with neighboring DSOs to reach a critical size is more advantageous. And last is the question of flexibility provider revenue. Would this flexibility provider receive sufficient revenue to ensure an appropriate deployment of flexibility? Task 2.1 of the SysFlex project showed that with a growing share of renewables in the system, the need for flexibility and capability to deliver specific system services will increase. Task 2.5 demonstrated that an energy-only market will not provide sufficient revenue in a high variable renewables future. Consequently, it won't make possible to cover investment costs and to ensure that there will be sufficient flexibility available in the power system. Task 3.4 reached the same conclusion. In one of the simulations, it is demonstrated that it is necessary to incentivize new investment in flexible technologies through strong investment signals via stable markets for the new system services. The risk of market saturation for certain services as fast frequency response were highlighted, and the study concluded that relying only on marginal cost pricing may not provide sufficient certainty for investors. Once again, attend the next webinar to see the detailed results of this simulation. So in task 3.2, we have described some market design solutions. For instance, the proposed long-term capacity product that can foster investment in new flexibilities if short-term markets are not able to provide these signals. So finally, as the marginal cost of energy will decrease in the future due to increasing levels of renewables in the market, it is of great importance to properly quantify revenue streams available for all sources of flexibility in order to adapt market design proposals adequately. This could imply, if needed, to create appropriate investment signals for both new entrants offering flexibility services and also existing service providers which can improve their flexible behavior. So thank you for your attention.
So thank you very much, all. It was a very interesting work that you presented, tried and summarized today on this, let's say, first part of the analysis of how, what would be the options to enhance the market design for the future power system with high levels of renewables. So it was really interesting. And as Hans-Peter said in the introduction, the full deliverable has been completed and it will be published very soon. So you will be able to have all the details of these analysis and studies. It will be available on the websites of the EU-SysFlex H2020 project. So you have the references here on the slides. So we had a couple of slides that I will address now to the speakers. There was a first clarification question from Quentin Boucher. It was on slide 14, please. And it was about giving some clarification about the capacity versus energy products. so addressed to Przemek, and asking if the description of services for capacity products is for the current state, or is it considering the coming NSOE platforms? And a specific question, so maybe it's the one after, sorry, is the one capacity vs energy? Thank you, yeah, that's the one. And why is MFRR not classified as a service both for capacity and energy products? So Przemek, maybe you would like to expand a bit on the response that you gave to Quentin?
Yes, thank you for this question. Basically, we used these services as the example to show explicitly what is the difference in concrete examples. So the FC, so we use the already existing practice that we think will be sustainable for the future. So the FCR, FFR, the capacity product only, the AFRR, RR for the both capacity and energy product. We had a problem with showing the examples of the system service with energy product only. So we've shown what we have, the existing wholesale market. So it is outside the system services market, but electricity market. We used the redispatching. It differs for between the countries, and in some countries it has only the energy product. When it comes to the MFRR, when we were discussing this product in our task force, we found out that in one member state, Estonia, this service is without the balancing, without capacity product. There is only product for the balancing energy. So we decided not to use this example for us. We decided not to use this service for the example of services with capacity and energy product. So basically, it's just the current state we selected. Yeah. Yes.
Yeah. No, so, thank you. I don't know if you wanted to add something else.
No. It's the answer.
Thank you very much. So I hope it answers Quentin's question. We have also a question regarding your summary and key messages for this first part, studying market options versus regulated options. And as we can see in the key messages in the summary at the end, you say that in this transition phase, for all countries towards increasing levels of intermittent and variable renewables, that sometimes regulated solution is the transitory option and maybe a long-term option. But how do we know how long this transition phase will last, and how to define really this transition phase and when it will end? Yeah, that's the one. Thank you. And how do we imagine that we can define that the transition phase is finished and that we can move to a functioning market-based approach? So maybe first this question would go to Niamh.
So I suppose for a given product, there might only be initially a small pool of providers. And also you might have the case that service provision is only proven from a subset of technologies, maybe only conventional units, say for a product such as synchronous inertia. So there mightn't initially be sufficient competition to have a competitive market for the product. But if you put in place interim regulated arrangements whereby you send out an investment signal out for that product and how it's valued. The industry then will tend to find technical solutions to enable it to be provided by other technologies. And so, for example, you'd have at the moment increasing amounts of demand response and batteries providing services. I suppose it's difficult to say exactly when the transition phase would end, but I suppose you'll know when there's an increasing amount of service providers with, you know, from different technologies, and therefore there's a better pool of service providers that you could actually have a competitive market.
Thank you, Niamh. I don't know, Przemek, if you would like to complete as well this answer from your point of view.
I will just do some advertising that it will be much more discussed in our deliverable of the flexibility roadmap. I don't remember what is the number of the task, but it is to be delivered.
I think it's work package 10, is it?
I confirm, yeah, it will be work package 10, yeah.
And it will be delivered in the second half of the next year, if I remember correctly.
Correct, yeah.
Yeah.
So thank you for the advertising for maybe a next webinar that will come next year. Thank you very much. And still on this page, maybe as we balance market-based solutions and regulated solutions, and we see that for different products we have different approaches preferred. So how do you see the coordination between market-based products and regulated solutions? How do you see them working together?
Okay, very good question. It depends on the circumstances. The easiest case is when we have different approach, but the data is similar, similar enough to use one algorithm. The clear example is enhancing the current cost-based regulatory approach for redispatching with possibility of involvement of distributed resources in this market. So we, on one hand, we have the cost data for the conventional units, and we would have the bits coming from the distributed resources. However, this data is basically the same for the optimization algorithm. So we would be able to solve it using one algorithm. However, it is, in both cases, is just the cost that need to be paid, but determined in different ways. For the distributed resources, it is that free bidding. We are not able to determine the variable cost. For the conventional unit, it would be the current solution. We could have the enhanced algorithm that deals with different approaches, or we could have several algorithms cooperating, one dealing with the market solutions, the second one with the regulatory approaches. They could be loosely tightened, they could be tightly tightened, coupled. So we have different approaches that will be that would be used depending on the situation.
Thank you. Thank you. I will move to a couple of questions to Philippe and Sylvie about the grid constraints. So first, I have a clarification question. So if you could explain maybe a bit more, how would well, any options, but in particular the centralized option work if you have only the sensitivity that you mentioned. I don't have the exact number of the slide, but you mentioned the sensitivity with partial grid data. So maybe could you clarify about a bit how could this work, please?
Yes, so it is the second, it is this one, okay, thank you. Donc indeed, this is an intermediate option. Here, the main data sent to the optimization operator is the set of sensitivities for the constraints to look after. That means that it is a list of constraints which have a realistic chance to be active. And so there will be sensitivities and margins. The margin is a difference between the current value of voltage or current and the constraint, and the sign of the value says if it is if the constraint is active or only potential. And you will see in the report that it needs an iteration, because both the sensitivities can evolve in function of the topology, but on the topology, but as well on the current evolution of the grid, of the injections and draw-offs on the grid, and as well the set of constraints to look after can evolve a bit. After an iteration, it is possible that a new constraint is to include in the set of constraints.
Yeah, thank you. It makes it clearer, and we can see in the report the compliments on this option. And maybe a more generic question, which is really interesting, is about how it is becoming crucial for any system operator to manage, aggregate, provide the data. Any management of the grid data is really central to the optimization. So how do you see this task of managing data for a system system operator? Do you see this task being really mandatory? Should it be a service that should be remunerated? And finally, are we sure that we can control, that regulators can control the right provision of grid data to a market platform?
So should it be mandatory? If in fact, if this optimization scheme is chosen, yes, it becomes compulsory. It becomes mandatory. There will be an exception if each system operator is own optimization operator. In this situation, when we say that the information is sent, in fact, it is the same information. Shall this information or this sending of information be remunerated? Yes, then it is the simpler solution is perhaps to include this task between all the current tasks of the system operators. It is not necessarily needed to foresee a specific remuneration. And I don't remember the third question.
Do we really think we'd be able, or regulators would be capable of controlling the provision of grid data to a market platform, to a market operator?
If I understand well, it links with the problem of confidentiality of the grid data. So I'm not a complete answer about it. So first, we can imagine mechanisms in which confidentiality of data is controlled. But may I remind that the most sensible data which need confidentiality are the data of the grid users more than the grid data in the strict sense. So it is a restricted information, of course, but perhaps less sensible than the other data that we have to manage in the current operation.
Thank you, Philippe. And to finish this Q&A question session, I have a couple of questions for Jan. So there is a question on the chat from Jan Eberbach, sorry. Are joint products only an option within a dedicated price zone, or is international market integration feasible from your point of view?
Well, generally joint products are of course also an option across borders. So there can also be a cross-border alignment of products for congestion management and for MFRR. When it comes to the optimization processes, as said, currently we see time challenges when it comes to optimization across scarcities. So currently we would say that this is not feasible. And then if you think of the cross-border optimization of both scarcities, then this would be even more challenging, but does not mean that in future it is impossible.
Thank you, Jan. And so lastly, the German use case did not reveal really convincing benefits or argument for joint procurement. In your opinion, and following how the analysis was carried out, how do you imagine the outcome could be different either for the German case or for other countries?
The outcome could be different in other countries where the price difference between congestion management and MFRR is a lot lower. So that could be possible that the created synergies outbeat the cost difference of MFRR and congestion management, or possible cost difference. It could also be diverse, that MFRR is cheaper than congestion management theoretically. So it pretty much depends on the national case.
Thank you, Jan. And maybe to close this as well, what do you see as system operator would be convincing arguments or benefits to implement the joint procurement? Because as we've seen in your conclusion, there are quite a lot of remaining challenges. So what would be in point of view of ESSO convincing arguments to move to joint procurement?
I think that, for example, those TSOs which do not see many congestions, there might be such joint procurement might be a good way to have simpler processes. So, for example, to have a joint bidding process and a joint product. So in the end, their transaction costs are cheaper. So in these cases, I would say that there are convincing arguments for joint procurement, as this is, for example, currently the case in France, where those requirements are mostly met.
Thank you very much. So as time is up, we need to close this webinar now. So I would like to thank all the speakers and the experts who provided the analysis that was presented today, and that will be very shortly available in the deliverable published on the EU-SysFlex.com website. The slides as well as the recorded webinar will also be available. So if some of your colleagues or even you, if you want to have access to these later, you will be able to have them on the website. Also, if you want to address more questions to our speakers, you can address them through the social, all the different social media of the project that you can see on this slide. So at EU-SysFlex on either Twitter, LinkedIn, or Facebook. And finally, I hope to meet you all again next week, as we will have the complementary webinar on Work Package 3, market design enhancement, and the results of all the simulation that we did for different options of market enhancements. So thank you again. Thanks Euractiv for monitoring this. And I hope to see you next week for next webinar. Thank you very much.